unutuyorum. Hı? Üç. Oh, sorry.
Okay, so last time I had given you some idea of corrections to muon decay. Today I will do another process to give you an idea of what a scattering process in weak interactions looks like. And then we will stop. That will be what you, up to the point where you should, that will be the material that will be part of the exam. Up to that you will be tested. As I said in the email, the exam is on Wednesday, and I've been told by Anil Ban that usually classes are not held in this coming week, so that you can prepare for that. So, but if you're going to be done with your exams by Friday, we can have a class on Friday.
Yeah, Friday we can.
No, Friday we have kept it.
No,
No.
Friday.
Friday we have
Oh, you have exam. Oh, acha.
Okay. Now, I had checked this with you earlier. I'm checking with you again, that you had group theory and so know the basics of that. Okay. So I won't spend time. I'll tell you some useful things as we go along, but I will not do a formal teach you everything about the groups that are necessary for us. But I'll assume that you have some familiarity with SU2, SU3. That is basically what we will need. Okay, so now let's look at a scattering process and weak interaction. So Fermi theory is, when I say Fermi theory, I mean this approximate theory that we are using, where we don't put in the gauge bosons that transmit the force and treat it as a contact interaction. Is that clear? That's the Fermi theory of weak interactions. So there, I want to look at the scattering electron scattering of a muon neutrino and giving you a muon and an electron neutrino. Okay. So weak interactions are signaled in many cases by the presence of a neutrino, because the neutrino doesn't have any other interactions other than gravity, which we don't worry about. So rather than calculate this in the standard way, I'm going to use crossing symmetry. Okay.
And the neutrino has interaction with gravity.
So anything that carries energy will have gravitational interaction, right?
It is massless.
No, but well, it's massless in the standard model, but it does have mass. I mean, it has been shown that neutrinos have mass. So that in fact is the most solid signal for some physics beyond the standard model that we have. But the standard model assumed them to be massless, but they're not. But the masses are very small, as I have said. Okay, so in this Fermi theory, this is a contact interaction. Okay, so as I had mentioned earlier also, see, scattering in gauge theory looks like this, but I shrink it and don't worry about the gauge boson. Okay. So my Feynman diagram looks like this. So E minus, I represent it by PA, then I have nu mu, and I represent it by PB according to my convention, and I have nu E, and that is K1, and then I have mu minus that I represent by K2. Is this clear? You're familiar with all these notations that I've been using since the very beginning. Okay. So get answer by using crossing symmetry applied to mu plus dk, which we saw last time. Okay. Last time we looked at this process. After doing muon decay, we said that it's the Cp conjugate of the process and so on and so forth, and has the same matrix element square as muon decay. Every particle was just the antiparticle of muon decay, which we calculated. So I want to use crossing symmetry here. Okay. So in mu plus decay, we had also labeling of the kind. This is mu plus, and for the template interaction that I want to cross, I put primes for that, okay, when I'm doing crossing symmetry. So well, let me write it here. So this can be PA prime. Then in my earlier one I had put this as K3. Now I represent it by a prime. And my nu E was, I think, K2. And this was K1. Is this clear? From last time. Okay, so first I put down the process I'm going to cross, and its momenta are labeled with primes. Okay. Now I have to get this process from this. So my mu minus has to go to the initial state, become an antiparticle mu plus. Okay. Then my initial nu mu will go to this side and become, looking at this. So my mu plus will go to this side and become this mu minus. and then this nu mu bar will go to this side and become this initial nu mu, okay, and this nu e will stay on this side, okay. And my e plus goes into the initial state here. Okay. Is this clear? Okay. So my mu plus with its PA prime goes to mu minus and has momentum K2. And my E plus with its K1 prime becomes E minus and has momentum PA. Then my nu E with its labeling of K2 prime becomes nu E, but here it is labeled as K1. Okay. Because coming from this current. Okay, this would be clearer if there were a gauge boson here. Okay, then the process would look like this. Okay, this would have to be a charged gauge boson. So this charge has to be conserved at this vertex, electric charge. So E minus, now this charge is being carried away by this W minus, which is negatively charged, and it hits the neutrino, gives it its charge, and you get a mu minus. Okay, so that's the actual gauge theoretic process, which I have shrunk to this point. Okay, and as I explained the reason, I'll repeat that this is a very massive object, and the propagator that you would write in gauge theory would have the mass square and some momentum square. And because this is the momentum square is much smaller than this is like 80 GeV squared, and the momentum being transferred in these low energy processes, I'm looking at low energy, where the electron energies are of the order of a GeV or something like that. So then this Q square can be neglected. This is then the propagator is a constant. The propagator is shifted into GF as a constant, absorbed there. And what you end up is a theory with only one contact interaction. Okay, that's the thinking behind all this. Alright, so here I'm trying to use this to get an answer on what have I missed on. Mu bar with its K3 prime goes to nu mu with labeling P. Okay. So now, as I said, whenever you change fermions from one side to the other, you will put minus signs. Okay. And then from spin statistics, you have a factor of -1 to the cubed because you are changing 3 fermions instead of 2. When you were earlier in the examples I gave you earlier, there were shifts of 2 fermions. So that spin statistics factor was not there. Now it will be here because there is a change. It's a 1 to 3 process on one side. So you're shifting things, 3 fermions. Okay, so this implies by crossing that PA prime in my old expression must be set to minus K2. K1 prime in my old process must be set to minus PA. K2 prime, my old process, will go to K1 with no sign change because the electron neutrino has not changed from one side to the other. Is this clear? Okay. And K3 prime becomes minus PB based on this and that. So earlier, from mu plus dk, we had sigma spins mod m squared equal to 128 gf squared PA prime dot K2 prime. I put in primes just so that it's easy.
What is GF?
GF is the Fermi coupling constant which has absorbed the mass. That's what we determined last time. Remember, we will determine the weak coupling constant by looking at the rate of muon decay. You were not there, I think, in that case. Okay. So now, make these substitutions and also multiply by minus 1 cube. See, if I make these three substitutions, I'll get a minus sign. Obviously, sigma sum square is not a negative number, but this additional minus sign arises because of the fermionic nature of the particles I am moving. Okay? I won't do this for bosons. So I multiply this by minus 1 also, since moving a total of 3 fermions from one side to another. So this implies that the sum over spins E minus no mu to no E mu minus is 128 GF squared K2 by K1 PA dot PB. Now, if you look at your notes, you will find that this is what this was, in the sense that the averaging factor of a half in that decay process was, when it was included, this was actually 64. Okay, so I have not included that yet in this expression. I am looking at a scattering process now. So there are two initial state particles, and averaging applies to the initial state particles. Okay. So certainly I have to put a factor of half to average over the electron spins. For the muon, neutrino, you have to be a bit careful, because at least in the standard model the muon neutrino is massless. So you will find that, and in the standard model it is always only left-handed. The state nu r is not part of the standard model particle spectrum. So let me explain a bit more. See, the normal Dirac spinner is a mix of L and R. Okay, where this is negative helicity, this is positive helicity. Okay, in the standard model, the neutrino is massless, and only this chirality exists in the particle spectrum. The other one is not there. So since the spins of these two are opposite, I normally include 1/2 for other fermions like electrons, muons, quarks, taus. For neutrinos, because it's not part of the particle spectrum, I don't include it. Now this is different from what I said to you about the fact that the weak interaction picks out the left-handed helicity. But I'm going to sum over spins anyway, because I'm putting in a projection operator for that left-handed spin. It will automatically remove the right-handed part, and so I can use the spin sum relation P slash minus M or whatever it is that way. That's a different thing. The reason for not putting a factor of half for the neutrino is because only the left-handed state exists for the neutrino, and the right-handed one exists for the antineutrino as part of the stipulated particle spectrum of the standard model. Okay, is that clear? Alright, so I'm going to put in only a factor of half for this, for the averaging. If this was something else undergoing a weak interaction, which had both left and right parts in the particle spectrum, so everything else, all the other leptons, electron, muon, tau, all the other quarks have both these as part of the particle spectrum. The neutrinos don't. Okay, so except for neutrinos, you would have put in another factor here for averaging. Okay, so it would be 1/4, like you usually have. Say in QED, E plus E minus going to mu plus mu minus and so on. You put in 1/4 for the averaging. Is this clear? So you see, you don't, when you're evaluating a cross section that nobody has evaluated before, you don't want to miss a factor of 2, because then you get a result which is twice as high or half as what it should be, and then people look for it and don't find it and say you are wrong. Okay, so you have to be very careful about these factors, because this will show up in the cross section, this factor. So now with massless fermions, I assume all of them to be massless. I just said 10 minutes ago that we are looking at low energy, but the energies are not that low that you can't assume these to be massless. Okay, so you are looking at some GeV energies, which is still a lot less than 80 GeV, 2-3 GeV maybe. But at 2-3 GeV, all of these can be assumed to be massless. Okay, so that's what I'm doing. So PA dot PV equals K1 dot K2 equals S by 2. Is this clear why this is happening? You've seen all of this, right? PA plus PV square equal to PA squared plus PV squared plus 2 PA PV. It's the same for K1 plus K2. And the masses are 0, so these things drop off. Okay? So, but PA plus PV is S. So the factor of 2 is taken to the other side, and this is what I get. Okay, so I get sum over spins because there is this S by 2 business. Okay, so there's a 4 that cancels the 128. Then I put an additional half for the electron averaging. So this is 16 GF squared S squared. Then I use my expression for d sigma by d cos theta, and I get GF squared S over 2 pi, where I'm using this expression. And if I integrate over theta, then my total cross section for E minus nu mu to nu E mu minus is GF squared S over pi. Cosine theta integration giving me 2. Okay, so just in case you have forgotten, the standard expression for d sigma was 32 pi e center of mass square d cos theta. Okay, that's used again and again.
Q1 and P are same.
I'm sorry?
There is a factor there. Q1 by P factor.
That's right. This is the final state, so it's the center of mass energy. This is this what you're referring? Oh,
That is
yeah,
the-
yeah. Q1 and P cancel each other. Center of mass, massless kinematics. Okay, so recall that from mu1 decay we derived GF's numerical value. That was 1.16 times 10 to the minus 5 GeV minus 2. So then I use the conversion. GeV is 0.389 millibarns. I'm doing this so that you become familiar with the language of particle physics, where you talk in terms of cross sections, okay, when you read papers or do something. So again, to remind you, one barn was 10 to the minus 24 centimeter square. So putting all this in, sigma E minus nu mu to nu E mu minus is 16.9 femtobarns. One femtobarn is 10 to the minus 15 barns. So you see, this is a very small cross section because there is this mass suppression coming from the heavy. The coupling constant is very small, it's 10 to the minus 5, and it's very small because there is a mw square in the denominator. Is that clear?
W square root.
So as I pointed out earlier, this q square minus mw square part is absorbed in GF. So this comes in the denominator because it's a propagator. Okay,
This is the propagator for gauge boson.
that's right, yeah. For any massive gauge boson, the propagator will be q square minus mw square, up to some gauge fixing factors and so on. Like for the photon, it was just q square because the mass was 0. Okay. So, sorry, this depends on the energy. I forgot that factor. Root S over GeV square. So this dependence on, all I've done is put in the dependence of S in this cross section. So I've converted these numerical things, GeV and so on, and pi's, and written this in terms of cross section units of femtobarns or centimeter square. So all these are interchangeable. Okay, cross section is an area. So centimeter square then in natural units is 1 over GeV square. And then GeV is some barns. So all those units have been used here to give you an expression like this. So that tells you that the cross section increases with center of mass energy square. Is that clear? Alright, so obviously the cross section is a probability for interaction. It cannot indefinitely increase, right, for an interaction with a small range of an interaction which is due to a force which has a limited range. Okay, so you can see that this kind of approximate theory is going to work only up to some energy range. When my energies get so large that Q square cannot be neglected compared to MW square, then I have to have the full theory to evaluate the cross section. So this is going to ultimately, if you extrapolate, you will get a huge number for the cross section. So this breaks down as you get to energies which are near the W mass. And you can see that because that's the approximation I made. I made the approximation that momentum transfers from one particle to another are much smaller than MW. Okay. Alright. So this is also writable. See, my root S is actually 2 E nu ME, where E nu mu is the incoming muon neutrino energy and the electron is assumed to be at rest. So there is a lab in the lab. The lab, what do I do? See, this electron is a target and a neutrino beam is created and it comes and hits whatever block of matter I am aiming the neutrino beam. In that block of matter, I assume that the electron is roughly at rest. Okay. So in that frame, root S is this, in the lab frame. Is this clear? Any question how this arises? Okay. You have, okay, electron is at rest. So my PA is ME 0, 0, 0. Okay. And then the neutrino is coming in the lab. So my PB is E nu mu along the Z axis 0, 0, E nu mu because it's assumed massless. Okay. So this actually has a ME square term which I neglect. So this is my root S here. And so in the lab, (1.7 times 10 to the minus 2 femtobars E nu mu over GeV. So the cross section is the same. Total cross section is the same in all frames, but I can write it in different frames. So here it's expressed in terms of the incoming energy of E nu mu in the lab. Okay. differential cross section is not the same as I have explained earlier also. The thetas are frame dependent as you boost from one frame to the other. Okay, so let's look at the spins in this case. So here's my E minus. Here's my nu mu. I'm looking in the center of mass. This is my nu mu. For the scattering, I just calculated. Okay, it's a weak interaction, so this has to be left-handed. So this spin has to be like this. This is coming in the center of mass from here, and it also has to be left-handed because there is a weak interaction which couples only left-handed particles. Then these guys go out. Okay, so I have mu minus, and that also has to be left-handed, and here I have nu E. Okay, this is going like this, also has to be left. They are all particles, so you can see that a spin 0 state is going to a spin 0 state. Okay, so this is a J equal to 0 scattering. As you learned, this is S wave. If the total angular momentum is 0, no special direction will be picked out. So you can see why the differential cross section I had. See, I had a differential cross section d sigma by d cos theta equal to gf square s by 2 pi. It's not dependent on theta because of this reason. Okay, you can't have a theta dependence. It's totally symmetric. Its angular momentum has no direction because its value is 0 both in initial and final states. Okay, so that's the reason why this is not so. In another situation, that would not be the case. D sigma by d cos theta would have some theta dependence in general. Is this clear? Okay, so this again gives you some practice in crossing symmetry as well as weak interactions, and does a scattering process in the Fermi approximation. Okay. So I'll stop here for today. This is the last thing that you need to prepare for the midterm. And we'll meet for exam. Yeah, 2 o'clock on 18th. Okay, so I'll see you here at that time next week. And I've given out the rules that you have to follow in the email. Very hard questions. Yeah. So, okay, so I hope that the questions will be fair, but they will not be totally trivial.
Yeah.
See, a good exam will require you to think a little bit more than what I have done in class. Okay? So I hope to set something that is not, that when you see it, you say, oh, where did this come from? I never saw this before, or he never talked about such things, and so on. So that's not a fair exam. A fair exam, if you sit and prepare the notes properly and know how to do the problems in the homework, you will not do badly. Okay, that's all I can say. So, I mean, that holds for the entire course. You study these, so the best way to do things, as far as, I mean, given the way I am teaching this course, is that you make sure you understand what's in the notes and in the homework, but it's not possible to understand everything from the notes. So you have to do related reading. If you feel, for instance, that you didn't completely understand this, then you go to Halson, okay, and look at his discussion of the same thing after studying the notes. Okay, so don't try to do something first from the textbook, because you know, I'm following some language, they follow some consistent way of doing things. So, but once you understand this, if you have understood something partially, okay, so you want to understand crossing symmetry better, then you go to, say, Peskin and Schrader or Halson and see how they are dealing with this. And that will supply what is missing, hopefully. Okay. So that's the idea. Now, a good particle physics course, of course, covers much more and lasts a year. Okay. I mean, it's good because I would have a second semester to teach you all kinds of other interesting things. But given the fact that most of you may not take such a course, even if it's offered, I have to give you, you know, all the important things in one course. So that means that I cannot just follow some textbook from page to page, because those textbooks are written for a 1-year course. Okay. And of course, Peskin and Schrader is at least 2 years or 3 semesters at the very minimum. And that, of course, well, it also basically teaches you QFT. But we would try to do maybe the first 5-6 chapters of Peskin and Schrader as far as material is covered is concerned. Okay, so that's the aim. And those are the 2 books that you will find most useful. So try to fill in gaps using that. Okay. But I would think that even if somebody doesn't do that at all, if you study the notes carefully and know how to do the homework problems, you should be okay. So you have to give it to someone.